Egocentric image captures hand-related activities due to our hand-eye coordination. As a result, egocentric images are taken under large hand motion, almost 90-degree pitch angle in this example. This is in contrast to upright scan image such as the one from ScanNet, where most of images are captured in the upright position, hence the geometry such as surface normal is well predicted. In this work, we study the problem of egocentric scene understanding, for example, predicting depth and surface normal from a single egocentric image. The challenge of predicting geometry for egocentric scene is as a large has motion. Our proposed method performs well on challenging egocentric videos such as Epic Kitchen. A geometry predictor must satisfy 3D rotation equivariance. Given a top view image eye and an upright image eye bar observing the same scene, difference in orientation between eye and eye bar induces the mapping between pixel x and wx. We denote the geometry predictors of image eye as phi of I and the geometry predictor of image eye bar at phi of I bar. The latter can be obtained by composing the former with a nonlinear transformation HW that is also parameterized by the relative rotation between I and I bar. In practice, the geometry predictor can be parameterized as a convolutional neural network. However, trained CNNs cannot guarantee 3D rotation equivariance. A spatial rectifier was introduced to preserve 3D rotation equivariance for CNN-based geometry predictor. Specifically, given a tilted image eye, the spatial rectifier transforms I into a rectified image that is gravity aligned, such that the CNN trained on upright images can predict well the rectified geometry. From there, one can reliably obtain the geometry of the tilted image by applying the inverse mapping. Egocentric images, however, involved with excessive perspective image transformation due to nearly 90-degree pitch angle when engaging in object interaction, which results in the significant performance degradation when applied the gravity-aligned spatial rectifier. We present a simple yet effective method called a multimodal spatial rectifier, a generalized gravity alignment to multiple possible directions of alignment. In particular, we decompose the surface normal distribution into multiple modes, where each mode represents a surface normal distribution of images captured from similar camera poses. This allows learning a coherent representation of egocentric images while minimizing the impact of perspective warping. As a result, our multimodal spatial rectifier produces a remarkable performance compared to the unimodal spatial rectifier. To facilitate learning the geometry from egocentric images with our multimodal spatial rectifier, we present a new dataset called EDINA, Everyday Indoor Activity Depth. Our dataset comprises more than 500,000 of synchronized RGBD images in gravity direction that was captured by 16 participants for the total of 16 hours, involving diverse activities such as cleaning, cooking, and eating. Our multimodal spatial rectifier produces strong performance on depth prediction. From left to right, we show image, ground truth depth prediction, and its error map. We compare with the standard training baseline on the bottom. On the right side, we show the gravity predicted from our network. Similarly, we evaluate the performance of surface normal prediction with multimodal spatial rectifier and the standard training baseline on the bottom. As evident, equipped with our multimodal spatial rectifier, the surface normal prediction achieves significantly better performance as compared to the standard training baseline. Finally, we show the performance of our method on the challenging Epic Kitchen dataset. From left to right, we show the depth prediction, surface normal prediction, and the gravity prediction. Our code and dataset are publicly available.